application that leads towards a homological interpretation for the color-Jones polynomials. So this is a plan for my talk. I will talk about color-Jones polynomials in general, as they're defined as quantum invariants. After that, the noise representation, which is a homological part of the story. In the third section, we'll see an identification between quantum representations and homological representations. And the last part will be about an homological model for the color-Jones. So first of all, as a motivation, so in general, quantum invariants are constructed in an algebraic way, starting with a quantum group and the representation of that quantum group. In our case, we'll use SL2, which is a quantum group of algebraic algebra. And to this thing and n-dimensional representation, we'll associate a quantum invariant, which will be the color-Jones polynomial. But this procedure of associating to this pair unique invariant is purely algebraic. And now the question is whether we can say something about the geometric description for this invariant. So this is what we have in mind. And what I want to mention is that for n equal to, G2 is actually the classical Jones polynomial. And here something interesting happens because we can describe it from UQSL2 and with a two-dimensional representation, but also there are skin relations. And for the Jones polynomial, Lawrence and Bigelow described an homological model as a gradient intersection pairing, but the proof uses the simulations. And now we were trying to do something for the color-Jones polynomial, which is defined directly from the quantum group, but it would be difficult to sort out the simulations part. So we are trying to do this using this input. Okay. Now we start the first section, which is about the definition. So we start with the algebra SL2. Now we fix Q a complex parameter. We define UQSL2, which is a quantum equivalent algebra. I'm not entering the details, but it's a Hopf algebra. And now we'll use representations of that. And if we take five-dimensional representations, they are in one-one correspondence with the natural numbers. So here for n, we'll have associated Bn, and that the relation is given by the dimension. Okay? So this is with for color-Jones we'll use this representation. But except that we have the so-called Verma module. So if we take lambda a complex parameter, we can define an infinite dimensional model which has a basis like this, infinite dimensional, with the following action. So K acts, in the UQSL2 we have three generators, E, F, and K. Here K acts just with a scalar.
What's K? Do we have to know this notation? I don't have to know this notation.
K's like, if you just think about the Lie algebra, K's like the
You have three generators.
the diagonal.
Okay, But do I have to remember that, or it's do I have to know
It's not necessarily in these details now, but I think what I want to say is that if I describe this representation here, if we take a special parameter, we'll recover the 5-dimensional representation. This is the idea. So here, the geometer x with q, the power lambda minus 2i, E will moves to the left, and EF will move to the right, but will multiply with a constant. Not as a constant, it's a scale which is f plus 1 times lambda minus I. Okay? And here x, q means qx minus q minus x over q minus 1. So this describes the model structure on this Verma representation.
So okay, so with the base elements vi whatever.
Vi hat, and these are.
What does it mean to move to the left if I equals 0?
It's just 0. It actually 0. So E v0 is 0.
Stefan, have you ever seen the quantum Randolph oscillator?
No. Perhaps I have, but I don't remember. I don't know how famous it was from here. Okay.
Okay?
Just ask you. Okay.
But I mean, it's okay that we say that E of v0 goes to 0.
So it doesn't have to be.
I mean, she's not telling you what relations these have to satisfy. There's some relations.
I mean, I
she's
don't want to enter
submitting
into
those
details. I just want to say roughly which are the actions, and there's a theorem that everything is well defined, and this gives you actually a representation over UQSL2. Okay, and now so this is for any parameter lambda. Now something interesting happens if we take the parameter lambda to be n minus 1, which is an integer. Because if we look at Vn here, Vn minus 1, sorry. If lambda is n minus 1, f will act with 0, because this thing will be 0. Which means that actually we gain a submodule in this Verma module, which is this will be a module of Vn, which will have the dimension n, so it should be isomorphic with the unique representation of dimension n. Okay, so this is Vn included in the Verma module Vn minus 1 hat. Right, so this is for the representation theory part.
So UQ SL2 is normally an algebra over C of Q, right? Just
Yeah, but I fixed Q a complex parameter, and I will vary afterwards. So if Q is a complex parameter, you could set it would be an algebra over C. Or I can, if I want, we can say that well we take Q a variable and we work over C of Q.
okay, and then you sort of embed all representations into representations over a larger algebra with a big complex one.
Yes, if I work over C of Q, yes, I have to be careful there right there. But if I specify Q to be a complex number and I work over C, I think that works. Okay, so having this info from the Vn and Vn hat, we'll really start the construction towards the Collet-Jones polynomial. So first of all, we have. So there are many things to say about this algebra and about all of these sections and so on, but I do not need to enter into details now because I don't have too much time. So I just want to take it as a back post and say just a few things about that. So there is a proposition that actually this algebra has a special element R, which is called the R matrix. Such that if you take any representation, we'll obtain a representation of the braid group Pn is defined on Vn is values in automorphism of V to the tensor power n. And here I say that the parameter sigma I goes to identity times I minus 1 tensor the action of the R matrix on V tensor V tensor identity n minus n minus 1. Okay, and this is a well-defined representation of the braid group, and this comes from the property of the R matrix. And secondly, we have an element in the algebra U such that we can define so-called dualities. So if we take Vn, we have the so-called evaluation, which goes from V tensor V star onto C. If I have V and W star, it's W star, but it's almost a natural action, natural function, but we act here with this element U. So it's W star applied on U V. And we have another function that we'll use, it's co-evaluation in the other direction. It goes from C to V tensor V star. And that will be the natural one. If you pick a basis, one goes to Vi to V star. Okay, and now we have the following theorem. So actually this data, so the representation of the braid group and the dualities, will help us to represent a functor from the category of tangles onto the category of representations of UQS. This is called the rationally derived theorem. So if we fix n, there exists a unique functor which is homological. FBN, which will be defined in the category of tangles. With values into representations. Okay, so here I will not enter into many details, but the category of tangles has as objects sequences of points with signs, and morphisms are oriented tangles between those sequences of points. Okay, and what we require from this functor is that FBN of a point with plus will be sent to V star. FBN of a point with minus will be sent to Vn star. And after that, we have the local relations. So if we see a cross like this is a morphism from V tensor V on V tensor V that will be sent into the action of the R matrix, which will act on the intercept length. And moreover, if we see a cut, that will be sent into the coevaluation. And in the other direction is evaluation. And these are the functions that we define here.
Here wrote V store, VN store.
They should be
Yes,
both V
yeah,
and
I'm sorry.
one should not have a store.
This is the I'm sorry. Okay, so this tells us a recipe so that if we have a tangle, we know how to associate a morphism from the tensor product V to the number of points which is downstairs to the tensor product of V to the number of points which is upstairs. And now with this very recipe we can construct a link invariant. Okay. So now the definition of the homology polynomial. So if you take a link, so first this will depend on the natural number. So for L link, we define Gn of L and Q to be this functor Fgn on M. And here we look at L as a morphism from the empty set to empty set. And we just apply the functor. So I will draw a picture. So if we have a link, the Reshtikin-Turaev recipe tells us that if we look at this link in the capital rectangles as a morphism from empty set to empty set, then we have just to see what happens. So we go from down and up, see what happens, compose all the morphisms, and we'll get a scalar. And this is the Cologne's polynomial. But now we can think to do something else. So there is the following theorem. So actually each link can be obtained as a flat closure of a braid. I will denote with double hat flat closure. Which means that we have 2 endpoints downstairs, 2 endpoints upstairs, and we connect 2 by 2 downstairs like this, and 2 by 2 upstairs in this way. And here is a
Sorry, can I ask a silly question? So what happens if you look at a knot as a long knot instead of, as a conversion from one point to
then you will get an endomorphism of Vn.
Yeah.
actually, but Vn from the representation theory they are simple. So each endomorphism of Vn will be a scalar times an identity.
Okay, so
So
it's the same.
actually you can get
It's the
the variant in that way as well. Okay, so a priori we have to start from this and go up to there. But now let's think a bit what happens if we take as a flat closure and we consider three main parts. This part, the break part, and the closure part. Now, if we apply the recipe, the empty set will correspond to C. If we apply the first duality, will end up into V to the tensor power 2n up to isomorphism. We'll get some V stars, but V star is isomorphism V. Again, we'll have here V to the tensor power 2n, and again C.
So what do you say about V star?
Sorry.
What
It's
is it?
isomorphism V.
We have a preferred isomorphism.
Sorry?
Like is this a canonical isomorphism or is it just
Yes.
one?
Yes.
Why?
Yeah, I mean, you can just define the isomorphism as a basis. You send Vi into Vn minus I star, and you check that that's an isomorphism. And here we get V tensor V star, V tensor V star, but I prefer to be quiet about that isomorphism and to write here just V to the power 2n. But later in all the details we have to remember this. That's wrong. Okay, so we'll have to, in order to do this construction, we'll have to compose the four morphisms that will come from this construction. And now here will come the natural definition of the weight space. So this is the third part, weight spaces. So if we fix n and m to natural numbers, we'll have the following definitions. This is just a technical part, so we'll take n minus 1 tuples, en minus 1, such that n of the numbers, the sum is n. Okay? And ENM n will be the same thing but with an extra condition that all the components are less than n minus 1. Okay, and now we remember that we have the Verma module and the finite-dimensional submodule inside. And we will consider the weight spaces with respect to the Verma module, which will be in correspondence with this set. And the weight spaces of the five-dimensional representation tensor n, which will be in correspondence to this space. So we have the following definition. WNM hat will be generated by VE1 VEN such that E1 EN is in ENM n plus 1 n. Okay, and this will be inside the Verma module to the tensor power n. So here we see that we do not have any restrictions on this coefficient that they should be less than n. But now if we want to look at the same thing but inside V n to the tensor power n, the problem is that we naturally will have a restriction on in the indexes EI, because all of them should be less than n. Because in the finite-dimensional representation we have just from E0 up to En minus 1. So we'll define VNM to be the same thing, VE1, VEN, so that E1 EN is the EN plus 1N. And that will be inside the finite dimensional module to the power n. So those are the weight spaces. And now we can define high-state spaces.
What's the difference between those two definitions? I can't tell.
Here's an n missing. Okay,
Yes. Yeah. So here we impose that all the components should be less than n. N minus 1.
So is the idea going to be that you're sometimes going to be coloring the strands with Verma modules instead of these finite dimensional?
Not exactly, but I mean, I'm not color just with Verma modules. The idea is that for the Verma module, we note that if you take the high-state space on the Verma module, that will be isomorphic with the noise representation. So it has the natural geometric side. And the problem is that if you color the strands with Vn, which are finite dimensional and live inside the Verma module, here we do not have directly a geometric side, and we have to construct it. And that's the main idea. So you know the weight space here corresponds to a geometric part, and you construct the corresponding part for this finite weight spaces.
So what is V hat?
It's a Verma module corresponding to
With
the
the hat.
parameter.
And the hat?
The hat means Verma.
The hat means Verma, and without hat means the
Standard
finite
finite
measure
dimensional.
representation.
So Fermat was the big infinite dimensional thing.
Oh.
That
Without
sometimes
that,
this
it's the
finite dimensional
dimensional
thing
somewhere.
sits inside. So it's, yeah.
No notation.
Yeah, I think I erased
Yeah.
that.
Yeah, okay. And why is it from Vn, not Vn minus 1?
Because this is a correspondence with a parameter. If you fix the parameter of the Verma module to be n minus 1, you gain n-dimensional submodule.
But it seems like
Because the parameter here is n minus 1, and if you put the parameter n minus 1, you gain exactly an n-dimensional submodule.
Yeah,
So
sometimes
it's-
these things are indexed by their highest weight, and sometimes they're indexed by their dimension. And I think that's the description, the
Okay.
discrepancy here.
it looks
It
pretty
is
odd with the
just-
KM. Okay.
Yeah, it's
Okay, okay, that's fair.
It's something silly.
okay. So now let's define the high-state spaces. So W and M hat will be just this VNM hat, intersected with the kernel of E, which will be the high-state space. And in the similar way, we'll have WNM, which will be the intersection with VNM with kernel of E. So we construct the high-state space in the Verma module tensor n, and the high-state space which lives inside this finite dimensional representation to the power n. Okay?
What's capital E? Couldn't have.
E is that operator that moves you left in the picture.
Oh.
It was the one that went to 0.
Yeah, okay.
Okay.
Sorry, how does it act on the tensor product? Does it act like Leibniz rule?
Well, you have an operator delta, and delta of E is equal to K plus 1 tensor E. So you have a commultiplication on your Hopf algebra, which goes from your Hopf algebra tensor into Hopf algebra tensor Hopf algebra, and use that in order to act on the tensor product. And you have a precise description of, which is a formula for that commultiplication. Okay. the interesting remark is the following. Why are we discussing about high-straight spaces? The remark is the following. Actually, when we have to compute that composition of the morphism, first of all we have to do the first morphism. So we start with 1. Doesn't work. And we want to go somewhere there in V to the power 2n. And the question is where we end up actually. So the key observation is the fact that if you take co-evaluation to the tensor power n on Vn, which is defined on C with values in V to the tensor power 2n, that actually will have the image inside the weight space. The weight space 2nn. So actually here on this picture, when we want to apply the first part is just the evaluation tensor power n. And this observation tells us that we can look just at the W to nn, because we'll end up here. And now, so this is why we have the weight spaces, and we have the Fourier proposition. So we said that we have the action of the braid group on this thing and on this thing. Moreover, these actions will pass to the weight spaces. So there exists a well-defined action. So first will be phi n m w hat, which will be defined in the braid group with values in automorphism of VNM hat.
Sorry, I'm confused about what's n and what's m. Where does I know the n is half the number of points, but what's the m?
Well, I mean, I'm just saying the weight spaces in general, but
So
we will
for
care
each-
just about 2nn. So in this geometric side, we'll be interested just in this part. But
Okay, so for
we
each
just
m
say
we'll
that
do this.
yeah, just I did that definition in general. Okay, so it's phi n m. So yeah, n corresponds to the number of strands, and m corresponds to the weight. If that's yeah, the fact that actually we put a condition that the sum should be m tells you that you have the weight which depends on m. Okay, so we have this action which is induced by phi on the homology, and a similar action on W for the finite dimensional thing. Which will be induced by the corresponding function. So from the restricting drive, we constructed representations of the braid group onto the Verma model tensor n and onto the Vn tensor n, and this tells us just actually those subspaces are preserved by the braid action. Okay. So this is the part related to the quantum definition of the Color-Jones polynomial. And now we discuss about Lorentz representations. Can I read here? we'll take the n to be this minus n point, and we'll take Cnm to be the configuration space of n points into the n. So puncture this, and this is C and n. And now we'll define a local system and take the covering corresponding to that local system. So we take the phi1 of Cnm. If we take the abelianization, we go to H1. And this is known that is Zn direct sum of Z. And after that, we compose this with the sum of this part, augmentation, direct sum of identity, which will go into Z direct sum of Z. Okay, so here if I have n components, I will just make the sum and write it here, and on the second component I have the identity.
The first n components are like linking numbers around each of those.
Yes,
complements
so
of those.
they're generated by the configuration when you make a loop around the puncture and you just preserve the others. And
What's the
this
second
one
Z? What's the second Z?
counts the rotation in the configuration space. So if you take how many rotations like this you have 2 points and you change the order in the space, but you are in the same point. Okay?
Is that kind of like the rhyme of a break? Or?
Yes. So we have these two morphisms, and now we can compose them and define phi to be the home position. And we will think about this Z and Z as generated by X and D for later part. And let's see an until. To be the covering corresponding to Kirchhoff. And here the projection. Right. And now we can look at the so the Lorentz representation will live inside the Borel homology of the covering. So if we take HM Borel of CNN with the coefficients.
So what's declaration here? H and what?
HM Borel-Moore.
What?
Borel-Moore.
I was supposed to know what that means.
So homology means local finite chains.
Okay. That's
With
easier.
with respect to the
Yeah,
market.
yes. I guess that's easier, yeah. Let's say it like that.
Okay. So we take this homology, and now that will be a module over the group ring of this. So I took the Z coefficients, so that will be a Z of Z plus Z module, which will be Laurent polynomials of n1 d plus minus 1. And moreover, now the braid group is a weapon class group of the puncture disk. That will act on the configuration space. So Bn will give an action on Cnn. And from the local system, we can see that will lift to the covering. So the braid group will still act on Cnn still. So we'll have a representation on the homology. And now we want to describe a submodule of this Borel homology. So this will be the second part, basis of multiforms. So we had that set ENM, which counted n-1 tuples with some m. So to each element E, which lives inside this, which can write E1, En-1, we will associate an homology class in this homology so-called finite chains in the following way. So here we have the punctures, and now we fixed n-1 numbers. So we can draw E1 parallel segments here, and continue this way up to En-1 segments here that meet just in the endpoints. And to this data, we can associate an homology class in the base space and also in the covering. So we consider Fe to be a map from Dm onto Cnm to be just if I denote these segments by I11, I1E1, and so on, I can take just a product of all those segments, and we'll obtain a map into the configuration space of m points, because the sum is n. The total sum is n, m. So Fe is the product of I, Ki. Okay? Right.
I don't understand what you call Ki.
So
Might be better to forget the subscripts and say that you just have this
I
bunch
have
of
I have
m
yeah
intervals.
I1 here up to IA1, and I will continue, and the last segment will be IM.
Yes, but for example, in those pictures I see from every, I see pairs of segments which are actually isotopic.
Yes.
So
Yes.
you consider them as separate segments?
Yes, I consider as separate segments because we want to end up in the configuration space, and this is why we take separate segments.
There are EI of them in the ice, in the ice batch of parallel segments.
So if we look at the punctures I and I plus 1, we take one segment, after that we do another one, we end up here. So, and in total we have EI segments.
Okay.
And we want to make the product of all of those.
What does it mean, product now?
Right?
What's in product?
Just as a, you think that the dm is being the product of m intervals, and you map each interval into the corresponding image here.
Oh, and that's
Okay, so in this way we'll obtain a map into CNM, and
I forgot what the configuration space is. You take the product minus the diagonal, but then what you do? You quotient by
the
the
action
action
symmetry
static
group.
group or not?
Yes,
Okay.
precaution. So they're not ordered.
So how's this mapping into the configuration space again? It's like a
So
disk.
you map into, so you map first into, more rigorously, you map into the product disk at the power m, and you quotient by the action of the symmetry group.
I mean, these are open intervals, right?
Yes, yes, yes.
product of all those intervals gives you a disk, and
Yes.
the product of the disk with itself a bunch of times, and then you're looking at its image downstairs in the configuration space. Is that
Yes. Yes. Okay. So we have
even though Stefan was really skeptical, I mean, it's very much similar to what you do in Hager for homology, for example,
That's supposed to help?
right?
Yes, of
Okay,
course.
helps all of us except for you.
That's it, okay. So, continue.
okay. So we have these homology classes. So we have these maps, and actually they will give you some classes into the homology with local finite chains. So that will give you. I will not also by FE, which will be in HM of CNN with coefficient Z. Okay? Okay. And now, actually, these maps can be lived. So first we have a map from BM of this configuration space, but that actually can be lifted. And this will be FE tilde, and that will give us an homology class in the volume homology of the covering. So we get FE tilde
So why is it a cycle?
in HM LF of CNM tilde. Those are coefficients.
Are you taking these are homology with locally closed chains instead of
Yes.
compact chains?
Yes, because the problem is that we have these punctures here. And we have open intervals, and this is why we have to take the homology with.
So FE tilde is you don't take all pre-images or all left of DM, not just one, you take all of them and then take a sum.
Okay, I don't want to discuss here about the base points, but actually
No, but that's what you do,
you have
like,
to take some base points. Actually, you take this, but you take actually also some paths, and you lift the paths, and you'll have a unique lift of this FE, which will be lifted into the list of the paths. I don't want to enter into details, but it can be done.
That is infinite sum.
I mean, the point is that you fix a point here, and you fix a path.
Locally finite nonsense.
No, I mean, the locally finite nonsense is to do with the fact that, I mean, the thing that she has is, a disk, right? I mean, it doesn't usually define that, wouldn't define a class in ordinary homology.
Yeah.
But I mean,
Oh, it's an open disk,
you
an
can
open
like
disk.
compactly support it.
Oh, I see the open disk. Then not.
Okay.
Originally by topology.
Okay, so we have this homology classes here, and we take now finally we can define the Lorentz representation. So definition, we consider the subspace generated by these homology classes inside the homology volume of the covering. Okay. Right, and this will be the Lorentz representation, and now we have a proposition. So actually, we said that the braid group acts on this volume homology, and now actually this will act in a nice way on this H&M. So we have an action of Bn onto this H&M. So we'll call LNM. Okay? And this is the Lorentz representation. Okay. I don't have time to say to say details for a dual counterpart, but I will just state a proposition. So without all the details, but just to show the fact that actually this homology enters in a pairing with another homology with respect to the boundary, called the Blanchfield pairing. So we have the following theorem. We have a pairing from this H to Mn, which will be generated by multiforks, by classes, by lifts of manifolds that are described by the multiforks. And that will be in duality with an analog space, but with respect to the boundary. So here we work with Borel-Moore homology, and here we will work with the homology of the covering with respect to the boundary. And we'll take some analog generators, but going in a vertical way. So for each E, we'll draw vertical lines. And we'll take the product of the vertical lines. And that will give us a class in the homology with respect to the boundary here, and that can be lifted in a nice way. And those two spaces are in a duality, which will go into Z of x plus minus 1, d plus minus 1. Okay. And now, which is because the third part. This is a Blanchfield pairing. Which is non-degenerate, I should say this. And actually, we can think at this thing as a graded intersection in the configuration space, and the intersection will be graded by the local system. Okay. And now, so we have on one side this Lorentz representation, H2NN, or HNM in general. But on the other hand, we saw previously that we had a breadth representation on this W NM, and in particular on this W to NN. Which is the relation between them? So this is a theorem due to Kono and Dito. So first we'll have a definition. They define a function phi, which goes from the index set ENM onto W NM set. So this is the weight space of the Verma module. So which will give you a basis here. I will not write down the expression, but we consider B to be phi of E for all E in ENM. This phi is very well defined and has a algebraic description. Okay, and using this, we'll define a basis in this WNM hat. And now we can consider using this basis. We can take the action phi nm hat. Just double hat, which is from Bn into automorphism Bn hat, but with respect to this basis. So for the Lorentz representation, we had the basis given by the multifolks, which are indexed by this set. And now we construct a nice basis here using this algebraic function, which is also parameterized by this ENM. And now the theorem is that actually the two actions coincide. So if you take PNM W of beta, which is the action on the weight space of the Verma module, this is isomorphic with the action of the Lorentz representation, LNM of beta, specialized depending on the parameter lambda. So somehow the Lorentz representation, it's good, and actually it encodes this action for any Verma module as long as you make the specialization with respect to the parameter that you chose for the Verma module. And this is on this side. So for example, if we take W2 and N hat, this theorem tells us that the action of the break group here is the same as the action on the Lorentz representation. Specialized.
So I've lost track of which of these indices keeps track of the original color I was thinking about.
2NN or?
Well, yeah, I mean, where do I see the color?
In the specialization, because here is Vn, so the lambda parameter here is n minus 1. And actually in the Lorentz side, we make the specialization with respect to lambda. So here x will be q to the minus 2 times n minus 1. Okay. So this is what it was known about the Verma module and the Lorentz representation. The problem is that if you want to do something for the colored Jones, we see that here we need to end up into this subspace of the weight space of the Verma module. So we have to do something else. We have to find the counterpart on the Lorentz side that naturally fits with this subspace. And this is what we do. Okay, so this is the last part, which is a homological model. now the parameter will be fixed to be n minus 1. We'll work just with that. And now let's talk a bit about the weight spaces. I will draw again. So here we're interested in W instead of W hat. And W hat is fits naturally with the Lorentz representation. So in general we have WNM hat, which by Kono and Ito corresponds to HNM, specialized in X's specialized in this way. And here we have a subspace which is WNM, which can be included in this one. And moreover, it has a complement. I'm not entering into details, but if we had VNM, that has a basis indexed by that ENM. And we can look at ENM with all components less than n, and ENM with where we know that at least one component is bigger than n. So we have a natural splitting on V hat, which will contain the corresponding V, and we cut with the kernel of E. And this will be a direct sum of this and something else. And the idea is we'll have a projection back onto W and N. And the question is what we have here. And the definition is, this is the first part. We consider H and N, which will be generated by lifts, but when we impose the condition that all the components are less than n. And in a similar way, we can define S and M bigger than n, where exists EI bigger than n. Okay, it's defined in a similar way. So in this way, H and M can be written as a direct sum. Okay, and which means that we'll have an injection and a projection back. So we'll take as a corresponding candidate for W and M to be this H and M N, which we included here, and also we'll have a projection onto that, because we have an orthogonal complement there. And now, which is a problem? So they might look that they are similar, but the braid group acts on the representation, but the braid group doesn't preserve the subspace. So what we do, we can try to force a braid group action and prove that it's a braid group action. So definition. So this is a good space. Here we'll have the good braid group action. So define LNM N on the braid group into to be actually, so we have this subspace here, and we want to act with a braid group. We can make the inclusion, act with a braid group here, because we know that the braid group acts here, and we can project back. We don't know that we don't know for the moment that that is an action, but we will use the correspondence here, and it can be proved that that's an action. So for the moment, this is just a function. Given by the projection composes actually a braid group onto H and M, composes an inclusion. now, well, we can construct having this inclusion, and we can go back here with a projection, which I will call pi nm w. Here we had the basis fe, we see e nm, and we can construct a set here which will be pi nm composed with pi composed with I of FP. So we'll transport the basis here, from here, going up, apply phi, and after we have to project. And we have a breadgroup action in this basis. Which we will call rho n. Random W. And now with all these prerequisites, know the following theorem. So first, the action that we defined, so the function that we defined lnm n is a breadgroup action. Secondly, this W, it's really a basis. This B is really a basis. And the third part is that the actions on that subspace of Lorentz and on this subspace are isomorphic. So rho nm W. This Lorentz. It's just up to n. Specialized. Okay. And now using this, I just take the conjecture how we can recover the color drops using this. We have a pairing between this H2 and N, specialized. I don't write the specialization. Tensor is dual into Z of T plus minus 2. The specialization is exactly the one that I wrote here. And then which will be a branch field pairing function. Okay, and the conjecture is that there exists a manifold F which lives inside here, specialized, and the homology class G in the dual space, such that if you take L and write it as a Platt closure of a braid, then the Color-Jones polynomial of L and Q can be recovered up to a scalar as a branch field pairing between the action of a braid group of F and G, with a specialization okay.
uncolored case, I mean, this must correspond to Bigelow's construction, is that?
Yes, so it should be something very similar to Bigelow construction. So I did not sort out all the details, but we have to see what corresponds to. So here in the two-dimensional case, you start with 1, and you go to a vector here, and actually you have to use this phi to see which is the first corresponding manifold. But it should be something that should be the Bigelow's construction. But I did not check all the details.
So, I mean, somehow his construction was asymmetric in the sense that on the one hand he had these things where he took the products of the intervals, but then on the other hand there were these sort of figure 80 things.
Yes.
I mean, is there, I mean, can I understand where that asymmetry comes from in this story, or is that an unfair question?
Yes, I do not exactly. I don't know exactly how to answer this question. So the difference is that here he took as a dual thing. The homology not related to the boundary somehow. And
Right.
this
Okay.
is
I
why
see. Yes.
this is,
Okay. Yeah,
and
okay.
he had a normal basis for that, and he used those manifolds, and he paired in that way.
Yes, I see.
Here, I think the construction might work with this kind of homology related to the boundary and take generators
Mhm.
the
Right.
barcodes.
Mhm. Okay, then I had another question, but, all right, so my other question was, like, if I look at the, my other question was specifically about true bridge knots, so 4 plats.
Yes.
So if I look at, the colored Humphrey polynomial of those things, so colored by sim, the sort of sim k representation, so the representation that's giving you this color Jones polynomial, then what I see is that somehow there's natural, I want to say that the colored Humphrey polynomial, colored Humphrey homology probably goes exponentially in the color.
Yes.
And so, I mean, I was curious if you could see, if you could see a similar behavior here in this construction.
So what happens when you increase the color?
Yeah.
Right. So here, when you on the geometric side, you'll have the same Lorentz representation, but when you change the color, you'll change the specializations.
So it's exactly the same representation.
It is the same representation, but you have to specialize in a slightly different way.
Oh, okay, that's interesting.
So this is the idea. Here you have the same good Lorentz representation. The only thing that changes, so here you can move the color, you change just the specialization.
Mm-hmm. Okay, but I see. But then your bases here, this sort of HNN with the big upper N in it is going to be different depending on.
Yes.
But,
So
okay.
also the subspace will grow.
Mm.
Yeah. You
Okay, I see.
include one into the other, and they will get bigger.
So do you know your conjecture for small n?
Sorry?
Like your conjecture, like for n equals n or 2 or so?
So for n equals 2, I guess it should be something very similar to a Bigelow's construction.
So little n equals 2.
Sorry?
The 2 n's which got unfortunate then. So little n equals 2.
Little n equals 2.
Or 3.
Yeah, I don't know how. For the moment, I don't make any computations for that because this is not finished yet. The idea is that I know. So for example, I know which is F. Because on this picture, you have to start with 1. And here you have just to take the evaluation, the co-evaluation, to the tensor power n of 1. So you know what you're doing here. And actually, the first manifold will be when you have this H2NN, and this is the phi that we defined in the previous theorem, this phi. Actually, the corresponding manifold will be just phi minus 1 of the co-evaluation tensor power n of 1. So I know precisely who is F. And now this theorem tells us, well, if you take the bread group action, you can either do this on the algebraic side, or you can do it on the Lorentz side, and you'll get similar results at this level. And now the last part is that here, in order to close the Color-Jones part, we'll have to apply the evaluation. And the part of the conjecture that still has to be done is that actually closing here with the dualities means on the right hand side to make a dimension pairing. This is still to be done. But everything is well defined, I think.
Any other questions? Let's speak again.